at distant ends hops along the shortest path. Node 3 status first before we can actually understand how to move packets towards node 6 as well as node 5 from node 4. So usually when that happens with only one iteration or one more or less one link to use for the transmission, when a particular node is out of one link or one path of the transmission, you use infinite value to represent it at its initial iterations. So keep that in mind. So in this case, if you want to get to node 6, it more or less becomes impossible. So we do have infinite value for it. The same applies to node 5 because you need to go through 4 to get to 5. But we're just only learning how the neighbors are interconnected first, or the state of the interconnected neighbors first. And we only have one iterations to work with, or one node or one link to work with. So we obviously can't get to 5 and 6 easily or currently. By the next iteration, what if we have two options or two links or two nodes to move a packet? So now watch, you notice that we can actually get to the farthest modes or the other farther modes of the network that we find ourselves in. So we do have 1 and 3 as our node or links that we can use to move packet across. So let's go through it real quick. So for destination 2, we still have the same thing. We still have 3. Can obviously go through from 1 to 2. It's about right. So we are using 1. And then for destination 3, same approach. We can still use 1 to 2. So 1 to 3 using 2 cost matrix. But look at 4 now. Look at 4 very closely. Keep in mind that Dijkstra is all about the shortest path, which means having the least cost. Okay? And since we do have 1 and 3 as our links possible that we can route a package through, ideally, these to go to node 4, it's much cost effective to go from node 1 to node 3 to get to node 4, which will give us 4 as compared to going from node 1 to node 4, which has 5. So 5 and 4, 5 is bigger than 4. So obviously, the most shortest path, which obviously has the least cost, associated with moving a packet from 1 to 4 now becomes 4, or becomes 1 to 3 to 4 instead of 1 to 4, because now we do have node 1 and 3 at our disposal. Very good. So what about 5? Now, we only have 1 and 3 as the link options that we can use. And it's pretty obvious that we cannot get to 5 from this point. Or we still can get to 5 from this point because we only have 1 and 3 at our disposal. So it means getting to 5 will still be what? Infinite at this point. Are we good? Still be infinite at this point because the only part we have is 1 and 3. And we can't get to 5 without going through 6. We good? And since 6 is not part of our node option that we have, or node links that we have, it's not going to be possible to reach 5 at this point in time. I look at 6. Obviously, we can get to 6 now. Before that, we had only one link, we couldn't get to it, but now we can get to it. And using the shortest path, or calculating the shortest path, we do have 1 to 3 to 6, which all falls within the two links that we have. That's 1, 3 to 6. So the cost there is 3, which gives you the 3 that you have for moving a packet from destination 1 to destination 6. But as you keep along, you notice that the more links that you have at your disposal, the better it is for you to get to all the other nodes within a network. Let's move to the third one. In this case, we have three traditional 3 links now. You have 3 options, which is to move the packet from node 1, 2, and 3. So like you have options now. You know, it's kind of like you going to a particular place and having various routes that you can use to get to that particular location without necessarily being stuck with just one route. So it makes it possible, it makes it very efficient for you to actually cut down time to get into that particular place within the shortest time possible or much faster because you have options. The more options you have, the better it is that you can route the packet to a shortest path or to a shorter path. Okay, so we have 1, 2, and 3 now at our disposal. So now if we want to get to destination 2, 3 is still the cost. So the shortest path to use. Destination 3, 2 is still the shortest path. Destination 4, still 4 is still the shortest path to go through by going through 1, 3, and 4. Now watch 5 now. Before, we couldn't get to 5. But now look, we can get to 5. Using what? The shortest path possible. And now we do have 1, 2, and 3. We have 2 as part of what? Our links or nodes that we can use. So in this case, we have 1, 2, 5. We can get to node 5 now from 1, 2, 5. Now keep in mind, we can also get to, okay, we cannot because we only have 1, 2, 3. So the only option we have now to get to 5 is from 1 to 2 to 3 to 5, sorry. In this case has got 3 plus 4, which gives us a 7 matrix cost or metric cost to get to node 5, which is great. So now pretty much we can get all the other nodes on the network. We get, but with only what? 3 nodes or links. Okay? And obviously getting to 6, same as 3. From 1 to 3 to 6. Now look what happened when we have 4 nodes now, or 4 links now to work with, or 4 paths to work with. You notice that the only minor change you're going to have is destination 5 has now got a much more least cost. In this case, since we do have 6 as part of the addition to our path, or possible path to use, it actually carries the least cost or the shortest cost or path involved. Keep in mind, let me point this out. In terms of the metrics that you see over here are just numbers that relate to the path cost. It's not so much about how many links am I going through. It's about finding the most smallest additional cost of giving links added up to help you move a packet from one source to one end, so from one end to another. So don't look at it more from just the I'm going through, since this is supposed to be the shortest, the Dijkstra algorithm is all about the shortest path possible. And you notice that if I want to get to 5, if we basically want to go by purely, by literally by just the shortest path. You'll notice that from 1 to 5, if you were to go 1 to 3 to 6 to 5, it's actually a longer path, right? Because you have 1, 2, 3 here, as compared to 1 to 4 to 5, or 1 to 2 to 4 to 5, sorry. So just keep that in mind. The cost and numbers you're seeing over here are just purely metrics that used to identify the uh, or that are assigned to the various links and their and how they move packets across uh, the respective links. Okay, so keep that in mind. So, anyways, back to now that we have 4, you notice that it's for 2 is the same 3, 3 is 2, 4 is still 4. But when it comes to 5, before that we only had 3, it was 7. Now when we have 4 options or 4 routes or 4 links to use, we do have a list cost of 5 now, which is great, right? Because the other path will give you much more higher cost. Okay? Like for instance, if we were to go from 1 to 2, which is part of the nodes anyways, to get to 5, we have 7. If we have to go from 1, we don't have 4 yet, so it'll still be infinite on this side. If you have to go from 1 to 3 to 6 to get a 5, which is part of it, it actually has 5. 2 plus 1 plus 2 is 5, as compared to 3 plus 4 is 7. So 5 and 7 change the ball game in terms of the shortest path possible to move a packet from A to 5. Now that we have 4 iterations, which includes 6. And 6 destination is always still the same 3. And from that point on, it's the same for all the least cost. Okay? Even though we added 4, so we have 5 nodes now, or 5 links now. So the same concept. That didn't change the least cost from moving a packet from A to 5. And from 1 to 3 to 6 to 5. Even though we have 4 now as an additional node to move the packet across. But if you notice, the cost involved in that path is actually 8, which is 5 plus 3, as compared to the 5 we're getting from using this particular path instead. Are we good, folks? So that's how the Dijkstra algorithm is executed. So in a nutshell, to summarize how these packets are moved across a Dijkstra algorithm, I moved across the network using the Dijkstra algorithms. You have your various links telling you for the first iteration, if you only had one notion or one link, it's all that you have. This becomes infinite to you. Okay. And if you have 2 iterations, which involves 1 and 3, you have more options. But now you've decreased the cost to get to 4. And the same applies if you have 3 iterations, 3 nodes or links. If you have 4. So generally, if you want to summarize the Dijkstra algorithm, you probably say that it depends heavily on multiple nodes and their status or their state to be able to come up with the most efficient and effective least cost path in moving packets across a network, which makes complete sense. So the shortest path, in summary, to move a packet uh, from one to all the various nodes across the network will probably be in this format right here. So to get to 5, the best shortest path to use is from 1 to 3 to 6 to get to 5. We good? The shortest path to get to 4 from 1 is still from 1 to 3 to 4, which is 4. As compared to, there was 5 away from 1 to 4. If you notice, was 5, right? And then from 1 to 2, 3, and what have you. So this will be a summarized shortest path diagram for moving the packet from one to all the various other nodes. After you put down your table, your gist diagram table or iterations, then you go to finalize your link state properties and to give you or to build out the proper shortest path tree that you need. Now, and what happens when there's a problem or there's a failure within uh, a given routing uh, a protocol using a gist algorithm, all based on the link states um, routing protocols or classifications. What happens? Well, when a link fails, very important to note this. This could be a really good exam question. So keep that in mind. What happens if you're within a gist algorithm and the link fails? What happens? Well, first thing is router sets their link distances to infinite, and then they flood the networks with an update packet, letting everybody know within the network, within the entire network, that hey, there's a problem, it's a link failure. So everybody should update the particular link that has failed. So all routers immediately update their link database and recalculate different short paths that are needed to move packets. Should in case other packets still comes through, you should know which other path to use to move the packet across without holding the packet too long or delaying the packet transmission by giving packet transmission. And then it recovers very quickly after that, but it needs to watch out for old update messages. So if there are old update messages, then it adds a timestamp or a sequence number to each update or to each update message, and then checks whether each received update message is new or not. If it's new, it adds it to a database and broadcasts it. If the message is older, it sends an update message on arriving links to inform the other links about the current state. So I'm going to pause over for now before we move on, because I'm moving on to distant vector routing. Okay, folks? So I'm going to pause real quick. Okay, so we're back. Let's continue with the distant vector routing. Distant vector routing, as we pointed earlier on, relates to routers only learning about the current states, the link states of only their neighbors, not the entire topology of a network that a particular router finds itself, shares its neighbors. That's all that important. So this is where you find routing protocols like RIP, which, like I said earlier on, I pointed earlier on, that are now widely used these days. Okay, so let's go through and let's figure out what kind of algorithm are also implemented within a distant vector routing implementation. Okay, so when it comes to distant vector, each node maintains a set of triples information, one being the destination, the cost for a particular link, and then the next hop. Since it doesn't keep track of all the uh, nodes within a given network, it's important to have a next hop to forward the message en route to its final destination. So hence the set of triples. Nodes know cost. Nodes only know cost to each neighbor. Directly connected neighbors exchange updates periodically on the order of several seconds whenever table changes. So when there are changes, minor updates here and there, the link challenges, link issues, then updates are periodically sent across to the neighbor nodes, so they can update their routing tables. Okay, and then each update, usually when it comes to the updates, they just list of pairs, which is destination and hops, because the assumption is your next hop are probably going to be the same. It's only when your link state changes that we need to update the destination and then the cost. So at least we know which uh, where a particular message is going to. So we can figure out different costs that we need to route that message um, through, or different cost path to route a message through. Updates are done to local tables if received with a better route, which in this case the smallest cost. And so they're coming from the next hop involved in that transmission. And then there's a refresh of existing routes to delete if time is out. So usually if update comes up and they show different, uh, much more smallest cost, then old routes are deleted, and as a way of uh, refreshing the database with current new updates. And also deletion can also occur when, of course, when a packet is doesn't receive acknowledgement. Then we know there's a problem with that particular link, so we delete that particular uh, link cost and update with new costs by refreshing the routing or existing routes within our routing table. So when it's a failure, so when it's a failure, it's all about neighbors updating uh, their neighbors about their states or the failure, or the challenge with a particular link, and then they update that information on their routing table. So how does a distant vector routing table looks like, or how is it executed? So let's go through a simple scenario where we'll look at how a routing table is set up for a distant vector routing. So key information that you need within your routing table for a distant vector is your destination, your next hop, and then the cost. So your next node or your next hop, the distance involved, and destination that you are moving the packets to. So here scenario we have, or example we have um, A to G nodes within a given network, and they've all been assigned a cost of 1. Each link is assigned a cost of 1 in terms of moving packets across it. So if you were to be on one node, and keep in mind here we're only interested in what? Neighboring uh, conditions, not the entire network. The question is, how would you determine the cost involved in moving the packets across the entire network? So if you're in node B and you want to move a packet to destination A, the cost is just 1 and you only have A as your next hop. If you want to move to C, same concept, you only have 1 cost and C as your next hop. But if you want to move a packet from B to D, you'd have to go through 2 costs and using C as your next hop. We do have the option of going from A to C as well. But since these are all just associated with only 1 cost, then we can just go from B to C to get to D. Okay? When it comes to moving a packet to E, the only options or the best option with the least cost probably be from B to A to E, which in this case gives you 2, and A happens to be your next hop. Now you do have the option to go from B to C to A to get to E, but that would increase your cost by 1, 2, 3. So ideally, from B to A to A to E, which is 2, having the next hop as A will be the best option to move a packet across from A to E. When it comes to F, same concept. A will be your next hop with 2 costs. And then when it comes to G, let's look at whether from using A, F to G will be much more cost effective as compared to using B to C to D to G. B to A to F, 1, 1, 2, F to G, 1 is 3. The same cost applies to B to C, 1, C to D, 1, D to G, 1. So that's 3 as well. So usually when you have scenarios like that where the costs are the same, you can just maintain one path that you feel it's less, has a better state. And then use that to move the packet across. So in this case, we're saying that to move a packet from A to G, we prefer to use or prefer to go from B to A to F, F to G, which involve 3 costs. Let's go into a much more in-depth illustration or iteration of how to build a table within a distance vector routing. Okay, you've probably seen a similar network diagram before from early on when we are going through the link state. But with this, especially when it comes to the distance vector, you're going to notice a number of difference in terms of how the routing tables are built by the various nodes. And once again, our main focus here is for each node to only understand the link states of its neighbors, not the entire network. We good? So, looking at it from each of the various nodes that we have in this setup, at the iteration level, at the initial stages, or at the initialization level, or you can say iterations for the uh, link states. Anyway, this one is more of initialization. So at A, our initial levels would have to move a cost. So to move a packet from A to itself would have zero cost, obviously, with no NSR. But from A to B, we have 5. From A to C, we have 2. From A to D, we have what? 3. But from A to E, if you notice, we have infinite. That reminds you of link states, right? At its iteration level, right? If you had only one link to work with. Same applies to initialization of a distant vector as well. At its initial level, getting to the farthest mode, it's not possible. But as it learns a lot more about the network over time, we'll start picking up some of the informations or costs that are involved in routing the packets to the farthest modes of the network, even though it's not essentially required within the distant vector routing to know the entire topology. So that's why we have the infinite mode over here, or infinite cost, with no next hop. When it comes to D, same concept. Obviously, D2 itself is 0, but D2A is 3, right? D2B will be infinite because it has to go through, because this is another side or another link of A, which it's yet to find out at the initialization level. So for now, it'll give it an infinite value. And the same applies to C. Keep in mind, this node is only learning about its neighbor's link, which is A's status at this level here. Not so much at this level or that level. Or sorry, at this link or that link yet. Just at this link. So hence the infinite value for B and C as well as for E. When it comes to B, same concept. To get to A, you have 5, reverse forward. B is going to be 0, itself is 0 obviously. C is 4. D will be infinite because it's on the other side of A's link. But E is on it's part of its link. So that's 3 to get to E. And then you come to E, and you start noticing some little changes within the next hops. To A to infinite because another link. B is 3 on this link. Now at this level, we can assume that A has come to understand that if it wants to move packets to other neighbors, it has to use a next hop, which is closer to its link as a neighbor. So hence you have the B showing up As a matter of fact, the next I can initialize as well for all of these. Okay, always start initialization at this point. We're going to build another one that has got all the next type illustrations. So for us to get to C from E, we have 4, and let's happen 2. Sorry, pin C. And then to E obviously is by itself. And this is a typo here, sorry. It's a typo right here. This shouldn't be, it should have a dash over here. So keep that in mind. Now, second, so now we've gone past the iteration initialization now. Now it's time to learn the various next hops of the various nodes that we have now. So now you notice that A obviously to itself is still 0 with no next hop. B, 5, I think it still includes some of the various next hop over here. Aside from C, aside from E having a C to its next hop. And the same applies to the rest of the tables for the various nodes as well. So this is the second time, like I said, we've gone past the iteration. So now we're building more or less a route cost of how to get to our various neighbors within this given network. So that's why you start noticing that the values started changing with various nest hops, especially illustrating the least cost involved in all the various nodes. So the nodes are updating themselves now with current link states, sorry, current link costs with the minimum cost, obviously, with the least cost anyways, and then there are next hops to achieving that least cost. So to note, in distant vector routing, each node shares its routing table with its immediate neighbors periodically and when there is a change. So if you were to update, so when it comes to updating the tables from the earlier point, looking at it from node A, if it receives a message from C, C gets updated with a next hop, compares it with other neighbors to identify which is the most effective least cost for a given for node A. So in this case, we're looking at node A here and how it updates its cost to have the least and next hop that it needs to basically forward packets across its neighbors to, to achieve the most reliable least cost distant vector routing protocol or service. So the most widely used distant vector routing protocol algorithm is the Bellman-Ford algorithm, which is practically what we just went through from this point on, from this to updates and more updates and comparing the updates. So finally you have a much more dynamically least cost involving moving a packet to all the various destinations within uh, node A's routing table. With the link states, we're looking more of the shortest path matrix, whereas with the distant vector, we're looking at the least cost matrix or metrics. So the Bellman-Ford algorithm is one of the most widely used one, and this is just an illustration of how it goes about it. The more dynamic or much more in-depth illustrations what we just went through with all these guys. So after n iteration or initialization, nodes at distance ends hops along the shortest path to have the correct information that they need to move the packet across. And as you proceed through, you start understanding how various sources and destination packets are moved. So basically, that should basically sum up everything that we need to understand about more or less, the overview of how routing is handled within most within the network layer of the OSI model. So as I indicated on the message I sent you guys earlier, um, we're gonna have a discussion on this. I have said a lot of stuff, within this whole presentation here. If you have any questions, we'll have the opportunity on either Wednesday or Thursday to go over them. So just go through it, um, jot down your concerns, your questions, suggestions, comments, whatever you have, and then we can go over it on Wednesday or Thursday. All right, guys, that's a wrap.